So, hi, Honors Chem people. So I decided to switch to this mode instead of doing the Google Hangouts just because I think it'll be easier for you guys, and I think trying to deal with connection issues and lag time and all the stuff that comes with Google Hangouts may be a bit complicated and lead to a lot of problems. But I will, like I said, I will be online. So if you do need Google Hangouts, just one-on-one or two-on-one or something like that, we can do that. But trying to get all of you guys on, I think it would just be easier to do it this way. So, I posted some homework for you guys on molecular geometry. Do it, practice it, make sure you guys are good with it. I also have a couple of other videos for you guys that I made for my other chemistry class that I'll post if you need a bit of a review or a recap kind of. You can look at those through Classroom. But this is going to be all about essentially hybridization, which we started talking about, and then all this chaos happened. All right, so let's jump into atomic orbitals and hybridization. So, I think it was chapter 5 was electron configuration and orbitals, but you remember electrons in individual molecules occupy atomic orbitals. Right? You have the 1s, the 2p, the 3d, and so on and so on. You can, calculate how many electrons and where they should be using that. You have your quantum numbers. But covalent bonds results from atomic orbitals actually overlapping and actually becoming different orbitals. Okay? So that's kind of what we're talking about. So if we have, remember, our s orbitals are just spheres, right? When they overlap, we get just kind of this darker spot right here. This here is our atomic orbital. If we look at our p orbitals, so they each have one electron, so one electron in this p orbital, one electron in this one, they overlap, and now we have this. What we can also do, we can also take a 1s orbital and one p orbital and get this sp combination. So you can have ss, pp, or sp. So hydrogen, right? Hydrogen is the simplest element. It has one electron in its s shell, and we have two of them. So its hybridization looks like this, right? They're spheres, they just overlap. Remember, this is a probability of finding electrons, so we've actually narrowed the probability to this region here for the bond, right? So they would have to be in somewhere in this range. Let's look at something like fluorine. All right, fluorine has 1s2, 2s2, 2p5. It looks like this. Remember, we have our px, py, and pz. Their overlap is right here. Okay? And so now let's look at a combination of them, right? So fluorine, its valence shells are the 2p, and the hydrogen is its 1s. So we get that sp overlap that we were talking about. Okay, so you've narrowed down the probability of electrons in this region here, which makes sense because if they're a bond, if these electrons are going to be shared, they're going to have to be near each other. So of course now we've just kind of cut down on the chances of finding them outside of this region. All right. So what we actually have to do, though, is so valence bond theory cannot account for a lot of experimental observations, right? So oftentimes what you'll see is we have to modify theories, we have to tweak theories, we have to adjust theories. Hold on. Sorry. We have to adjust our theories. We have to say, okay, this doesn't work. We need a new explanation. And that explanation leads to new theories, right? So if we look at our beryllium dichloride, right, beryllium in the center, chlorine in the middle, According to Vesper, both bonds should be linear and both bonds should be equal. So beryllium has 2 valence electrons, no unpaired. Right, so this is our hybridization, right? So we've bumped an electron up to the 2p1. This star just means it's in an excited state because we've added energy. So we have 2 types of overlap with our 2s and our 2p. Okay, so we have 2s and 3p, and 2p and 3p. They're just saying these are not the same thing. So what we actually get these hybrid orbitals. So these orbital shapes are pictorial representations of wave functions, which, if you remember, they're mathematical functions, right? So we can get SP hybridization. So the mathematical wave functions, it's a lot of calculus. It's a lot of calculus 3, actually. A lot of what we're not doing in this class. But just know that just like when we're doing atomic orbitals, we had probability. It's probability here. You can use math. You can use computer modeling to kind of predict a lot of things. So if we look at our beryllium, right, we can actually hybridize. So we can combine their sp orbital and put 1 electron in each. All right. So the 2 sp orbitals point in opposite directions in line with one another. So that's this one and this one. Okay. So this is what they look like, and then you have your normal orbitals here in the white. Right. So each beryllium sp orbital overlaps with a 3p orbital and the chlorine to get a BeCl2. So chlorine 3s2, 3p5, beryllium sp, we get this. We get this linear structure, and all bond angles are 180 degrees, right? Because it's linear, that's what happens, right? So what happened is each sp orbital overlaps 1 3p orbital of the chlorine to yield this. Okay. Let's look at BF3. Let's look at a different example. So trigonal planar, all bonds are equivalent. All right, so boron, 2s2, 2p1. 1 unpaired electron. So we can do the same thing. We can hybridize again, and we can get 2 overlaps with 2s and 2p because we have another electron right here that we didn't have in the last example. All right, so what we get is we get this. So sp2 orbitals overlap and form a triangle. Okay, boom, boom, boom. So instead of just being linear, they are like this. They form this equilateral shape. Okay, these are sp2 hybridized, we would say. Okay. Now, so again, each sp2 orbital overlaps a fluorine 2p to get BF3. And so you can see now we have our fluorines, we have our equilateral triangle. All right. With sp2 hybridized. You can also do sp3 hybridization. All right. So our carbon, 2 unpaired electrons. We can hybridize, and we can get 1 in the S and 3 in the P. All right. So now we're using 2s, all of our 2p's, so we get this sp3. Okay. 1s and 3 p orbitals. So this number, this sp2, sp1, sp, is the number of p orbitals. Right now we only have one s, right? Because every electron shell only has one s orbital. But you have 3 p orbitals, and you have 5 d orbitals and 7 f orbitals. Right? So we get this tetrahedral structure, which is a little hard to see because it's pointing in the back. But this is what you get. You hybridize the carbon, so now you have 4 sp3 orbitals. Okay. And hydrogen only has one s orbital. So you get 109.5 degree angles, and you get this tetrahedral methane molecule. Okay. So you have sp3, sp2, and sp1, which is just the number of p orbitals, essentially, that you're using. Okay. Now, we can take it a little bit further, and we can do the d orbitals, which is how you get things like these expanded octets. And what they mean by expanded octets is you're breaking the octet rule, right? So phosphorus, the octet rule says 8. But this has 2, 4, 6, 8, 10. It's because you can actually hybridize d orbitals, and you can bring them into the mix and get things like this. All right, I am not going to be too concerned with you about knowing anything past sp3. Okay, SPD gets very wonky and confusing and not worth you spending too much time on. But I want to show it to you so you understand why you see exceptions to the octet rule. It's because, oh look, phosphorus and chlorine have just sp3d hybridized. Okay. So, if you notice, if you have 2 electron domains, you have sp. If you have 3, you have sp2. If you have 4, you have sp3. So if you notice, the electron domains is 1 more than your hybrid orbitals. Okay? So if I give you a question and you're not on a quiz or a test and you're not sure, if you have 4 electron domains, you're going to have sp3 hybridization. If you have 3, you're going to have sp2. And 2, you're just going to have sp. So keep that little trick in mind for homework and things, that you can essentially use this as a little shortcut of 1 more electron domain than hybridization. Like I said, I'm not concerned with this. I mean, you can even do sp3d2. Yeah, ignore this. No, up to here. Okay? So, Lewis structure, you can do electron domains, you can do molecular geometry, and you can also get to hybridization. All right? So, that's going to be it for this video. The next one will be multiple bonds, like double bonds and triple bonds and fun things like that. Okay? So I have some homework posted that will be released, and I'll have some things. I want you guys to take notes, and I'll have a post on Classroom about what I want for that for you guys. Okay? So go back, watch this video. If you have questions, reach out. And I will hopefully see you guys in 2 weeks. I hope we don't have to go past that. All right, enjoy your day, guys, and enjoy the time off a little bit. All right.